So thank you, Clara, for the introduction and for organizing. I hope you've been all having a great week and learning a lot. Yeah, so I will be talking together with Lorcan, who's already a doctor, about a classical and quantum cryptography. So this is partly what I do research for in my PhD. I work a lot on this type of protocols called quantum key distribution protocols, which we will talk about a little bit today. And also, I think on Friday and on Thursday, you will be doing some experiments with quantum key distribution as well. So yeah, in preparation for that, I hope that today I can give you some of the fundamentals about quantum key distribution and more broadly in classical and quantum cryptography, so that you guys can understand what it's used for, the kind of level of rigor that it requires. Right, so let's get started. So as a little bit of a top overview, first I'm going to give a motivation for quantum cryptography, for cryptography in general, what it's used for, the kind of rigor that it needs, etc. And then we're going to be moving on to a quick review of concepts that we need. In particular, we need to know a little bit and be reminded a little bit of some probability theory, some simple stuff here, only take 5-10 minutes. And from there, we'll move on to classical cryptography. We'll see a couple of examples of security definitions, and in particular, a protocol for classical cryptography. And then we'll move on to quantum cryptography, and in particular, quantum key distribution. At the end, I will let you choose from a couple of different quantum key distribution protocols that you would like to learn about. And if we have time, maybe we can even do both. Okay? So let's get started then. What is cryptography? Has anybody dealt with cryptography? Do you guys know, or have you heard the word cryptography before? Yes, no, maybe? Yes. Yes, okay. So what is cryptography then? So cryptography, you can think of as the study of sending and receiving messages in a private manner, perhaps in the presence of some sort of malicious party, adversary, or eavesdropper that would like to gain information or somehow act in an adversarial manner in like your communication program. Usually in cryptography, we have these toy parties that represent the parties of a cryptographic protocol. This one is called Alice, this one is called Bob, and the spy, the adversary, is sometimes called Eve. Okay, E for eavesdropper. Right, so one example of a cryptographic protocol concerns the secrecy of communication. Right? In this particular example, Alice wishes to send some message to Bob, some message M, in such a way that the message that is sent over the public domain cannot be inferred by a potential spy E. So basically, Alice in some way wants to obfuscate her message so that no spy can gain any information about the underlying M. Okay, so let's get a little bit of the nomenclature for cryptography nailed down first. So the message that usually we want to send is known as the plain text, right? This is simply the message that Alice wishes to communicate to Bob. The encryption algorithm is precisely the algorithm that is used to encrypt the message, right? So usually the message or the plain text goes by the letter M, is put through an encryption and produces a ciphertext, right? Which is just the input of the encryption algorithm. Usually this is exactly what you want to be hidden, right? Or to have the property that it hides the message. You use a decryption algorithm, which is what unencrypts the ciphertext and gives you back the original message, or hopefully gives you back the original message. So cryptography actually dates back to a long time, right? It was in the interest of history, right? There have been many cases in which parties needed to communicate. For example, think of two parties at war, right? You want to be sending messages to maybe the spies that are under enemy ranks in such a way that the information between the messages is not even captured, cannot reveal any information about like secret attack plans or something. One of the oldest known examples of cryptography is known as the Caesar cipher, right? Dates back to the Roman times. In the Caesar cipher, it's a very simple cryptographic protocol. You take your alphabet, right? And you shift the location of every letter by a certain amount, right? The shift, the amount of places that you shift each letter by is the key of the algorithm, right? And the encryption basically takes in each letter and to the corresponding one after everything's been shifted. So I think in this particular case, everything is shifted 6 places to the left. So like A is here, and now A is over there. And basically you just replace each letter in your message word by this key. Now we will have a little demonstration with Lorcan here to kind of demonstrate how the Caesar cipher works.
Yeah, so I have a very simple wheel for everyone. I'm just gonna take one. Oh yeah, sorry. So if you take one big and one small, and maybe work in groups of 2, and then pass them along. But basically, everyone is going to have inner wheel and an outer wheel, and then you can line them up and stick a pen or pencil through the middle. So for example, it's probably hard to see, but if I was,
Yeah,
please. Okay, now so you take your little wheel and line them up, and you put your pen through the middle. And essentially this lets you very easily map any set of letters to another set of letters. So if, as Enrique is talking about, we have the key of 0, then you would be mapping A to A and B to B. In this case, you can map A to G, which basically means that you line up the letter A with the letter G, and then any message that you want to encrypt, you just read off this wheel. So for example, can anyone encrypt hello using this mapping? So you line up the letter A with the letter G, and then you can read off how to map out hello. You have one letter for H, another for E, etc., etc. The first team to get hello wins a prize.
Okay, so we have a team that has solved it. What is it? Show it. So if I could get everybody's attention. Right, so we have a team that has successfully encrypted the word hello.
So I believe it should be MK or
RRU.
RRU. And the prize is available to everyone back.
So thank you, Lorcan. Right, so now question for everybody. This form of cryptography, the Caesar cipher, is it secure?
Oh.
No, why? You can brute force it. How can you brute force it? Precisely, right? So to everybody who didn't hear, basically what you can do if you receive or manage to capture a Caesar cipher encrypted message that reads like gibberish, you basically try every shift. There's 26 of them until you manage to decrypt something that makes sense. Okay. And then you know the key and you can unencrypt subsequent messages. So basically this highlights the importance of proper definitions and proper security when you're defining cryptographic protocols. You cannot just come up with any old way to encrypt and hope that because it's sufficiently hard to do maybe for you, that nobody will be able to do it, right? When you come up with a cryptographic protocol, we have very standard definitions of what it means to be secure and very strict definitions of what the adversaries can do to break these protocols, right? So cryptography, in truth, is a very mathematical subject for this reason, right? As you would want it to be. Cryptography is used for everything, to protect your messages, to protect your banking information, healthcare information, to protect communication between, say, governments or companies, etc. So there needs to be it needs to be very regulated and very well defined per se. So cryptography, in fact, is a very mathematical subject. As we have just seen, you need to have very strict definitions and notions of security and eavesdropper power. So with this in mind, what can we actually use cryptography for? So the example that we just saw pertains to one aspect of cryptography known as privacy or confidentiality, right? The protocol that we have just been looking at is to obfuscate a message, right? To basically keep communication between two parties secret. But in fact, cryptography can be used for a lot more. So for example, We also care about integrity of communication in cryptography. What is integrity? Well, it's the ability to detect unauthorized alteration to communication between parties. An example would be if you're messaging your friends and somebody manages to intercept the message and just changes it. Ideally, you would want this change to be detected, right? We also care about authenticity, which is to confirm the identity of a sender or a receiver, right? For example, if two governments are communicating, you don't want any third government pretending to be one of the two original governments and say something, say, malicious, right, or non-malicious. And lastly, we also care about non-repudiation, which is to prove that communication was received. In a way, you can think of this as a form of signatures, right? Non-repudiation means that your messages come with a signature that cannot be forged. So that, for example, you cannot lie to your bank and say that you have not received an amount of money when you in fact have received it, right? This is the exact kind of thing that non-repudiation will be used. Right, so as mentioned before, cryptography needs to be very mathematical because we need rigorous definition of what it means for a protocol to be secure. And more importantly, we need proofs that such protocols satisfy these security definitions. Additionally, we also need to properly define what malicious spies, adversaries, eavesdroppers can do. And again, we need concrete proofs that a protocol behaves as it should, even with adversaries around. So this kind of concludes the introduction. Now we can get on to the fun stuff, the math of cryptography. Okay. So as said, we'll be quickly reviewing some concepts of probability. This shouldn't be super hard. So hopefully you're all familiar with everything here already. So what is a probability? A probability is a function that maps so-called events to a number between 0 and 1, right? An event is just something that can happen, the flip of a coin, the roll of a dice, etc. And a random variable is simply a variable whose outcomes are the possible events. So for example, in a roll of a dice, the possible events are any combination of outcomes. A dice can roll a 1, a 2, to a 6, or it can also run a 1 or a 3, etc. Right? A random variable x in this case would denote the outcome of the dice. So then you can make statements about what's the probability that a dice rolls a 1, or what's the probability that a dice roll is less than 4. Okay. In cryptography, we're also interested in so-called joint probability distributions, which are basically functions that consider more than one random variable at a time. So here we have a random variable x that can take some event omega x, and some other random variable y that can take another event omega y. And the probability of the joint distribution of these two random variables basically tells you the probability that these two outcomes happen at the same time. So for example, suppose that x is the outcome of a 6-sided dice, and y is the outcome of a fair coin. Then it makes sense to ask questions of the type, what is the probability that the dice rolls a 1 and that the y is a head? Well, since these two events are independent, the probability that a dice roll is 1 over 6. Why is it a third? Yeah, I think that's a typo on my side. It should be obviously a half. Because yeah, if you flip a fair coin, the probability of a head is a half. Likewise, we can also ask questions about what is the probability that a dice roll is less than 3, and why the outcome of a coin is either heads or tails. Well, what's the probability that a dice roll is less than 3? That's a half. Why? Because it can be 1, 2, or 3, which is half the outcomes. And what's the probability that a coin gets heads or tails? Is 1. It should be either of them, right? So from joint probability distributions, we can also learn about conditional probability distributions, which basically tell you the probability that something happens given that something else has already happened, right? So in this notation, we're considering the probability that x is some event, omega x, given that you know that y is some event, omega y. And the way you calculate this quantity is by considering the joint distribution of x and y happening at the same time, and then divided by the probability that the event Y that you're conditioning on has already happened. Okay, so that's an example. Suppose that in Singapore, it is cloudy with probability 0.5. So any given day, it is cloudy 50% of the time. Okay. And suppose that during cloudy days, it rains with probability of 0.8. Then we can ask, what is the probability that on any given day, it is both raining and it is cloudy? Well, we're precisely asking about a quantity of this form. So we can just rearrange the two terms, right? The probability that it is raining and it is cloudy, it is the probability that it is cloudy, which is the denominator here, times the probability that it is raining, given that it is cloudy, which is the quantity on the left-hand side. The probability that it is cloudy on any given day is 0.5. And we know that if it is cloudy, it rains with probability 0.8. So this is 0.5 and this is 0.8, multiply them together, and then you get that the probability that on any given day in Singapore, it is raining and cloudy is 0.4%. I think that's pretty close to the actual answer as well. Right. That's it. That was all the review that we need to know for this lecture, easy peasy. So next, we're going to be talking a little bit about classical cryptography. In particular, we're going to be focusing on protocols that pertain to the secrecy of communication, right? We're not going to care about the authenticity, non-repudiation, stuff that we mentioned before. Right. So classical cryptography is essentially the study of any cryptographic techniques that use classical algorithms, right? Classical techniques. And by classical here, I mean everything that is not quantum. Okay. So broadly speaking, there are two types of classical cryptography when it comes to security of secrecy of messages. Firstly, secret key cryptography, also known as symmetric cryptography. In this case, both the sender and the receiver have a singular key, right? They share the same key. They both know the same key. And they use this key for the purpose of encryption and decryption, right? So suppose I was to communicate with Lorcan. We both have a copy of the same key. I can encrypt my message using this key. I send the ciphertext to him, and then he subsequently decrypts the ciphertext using the same key. Okay. Of course, there are some problems with secret key cryptography, like how do you distribute the keys, right? Like you have to assume that the key that he has is the same as my key, that nobody has found the key in transit from place A to place B, etc. Actually, fun fact, in practice, for very high security applications, the National Security Agency of the United States will literally fly people with a briefcase containing secret keys to the location where they are intended to be used, so that nobody else can guess them in the meantime. So they don't want to risk it being transferred over the internet or over mail. They will literally fly somebody with a briefcase containing secret keys. Alternatively, we can also talk about public key cryptography, also known as asymmetric cryptography. The discovery of public key cryptography in like the 70s, 80s, basically revolutionized how we think about cybersecurity and information technology, right? It's a much more efficient way of achieving security of communication or non-repudiation, authenticity, integrity, etc., in a way that is practical to use, especially over platforms like the internet. In public key cryptography, the difference is that everybody has two pairs of keys. The receiver has two pairs of keys in particular. Now, suppose Lorcan is the receiver of a message. He's got two keys, a secret key, which he keeps to himself, and a public key, which everybody can see. If I wish to send a message to Lorcan, what I do is take his public key, encrypt my message with his public key, send the ciphertext to Lorcan, who then uses his secret key to decrypt the message that was encrypted with the public key. This is why it's asymmetric, right? So everybody will have two sets of keys. If you want to send a message to me, you look at my public key, and then I decrypt with my secret key. If I want to send a message to Clara, she's got her own pair of keys, public and secret. Okay? It's obviously much more practical because now you don't need to transport keys. Everybody can just generate their own keys. In particular, we're going to be focusing on secret key protocols because they're a little bit simpler than public. Symmetric key scheme for secrecy of communication usually is composed of three elements. Firstly, you've got a key generation algorithm, which we usually call gen. Basically, this it's a little bit of technicality, right? The generation algorithm basically takes a security parameter, n, and outputs a key to be used for the protocol. This security parameter you can think of, for example, as the literal length of the key. If your security parameter is n, then your key will be a string of n numbers, for example. Okay, that's not exactly how it works, but you can think of it that way. Then you have the encryption algorithm, which takes in the key that the generation algorithm generates, as well as a message that you want to encrypt, and outputs the cipher C. Symbolically, we write that encryption taking in the key K and the message M outputs the ciphertext C. Lastly, we have the decryption algorithm, which takes in the symmetric key and the ciphertext C and outputs a message M dash. So symbolically, the decryption algorithm takes K and C and outputs M dash. So what are the properties that we want this general cryptographic scheme to satisfy? There are two properties that I'm looking. Any guesses? Once again? Yes, so that is a property that this has, but it's that property from definition, right? This algorithm generates a K, and it's both used in encryption and decryption. But that's not one of the properties that I was looking for.
It's very hard to reverse the encrypted message without the key.
Precisely, that's the property of secrecy, right? That if an adversary finds out C, it's hard to get any information from M given C. Okay, and what's the second property that we would like this to satisfy? I'll give you a hint. Look at the inputs of the encryption algorithm and look at the output of the decryption algorithm.
That it will always produce the same output.
Yes, precisely. You want it to satisfy the property which we call correctness. You want the output of the decryption algorithm to be the same as the input of the encryption algorithm. In general, when you're dealing with functions enc and dec, which are probabilistic, then this might not always be satisfied. Okay, but you would like it to be, right? So precisely, we want our cryptographic scheme composed of the algorithms gen, enc, and dec to be correct, which basically means that the decryption using K, taking in a ciphertext produced by the encryption the encryption given K and M to be the same as M. Okay, does everybody understand that notation? It's just composition of functions. You apply the decryption on the encryption on M. Okay, and you want the output of that composition of functions to be the same as M. So in a way, you kind of want dec to be the inverse of enc, in a sense, as opposed to public key, in which the encryption takes in the public key and the decryption takes in the secret key. And secondly, we want to satisfy the secrecy property. And to put your idea into mathematical terms, what we want is to say that a cryptographic scheme is secret, perfectly secret, if for any message M and for any ciphertext C produced by the encryption algorithm, the probability of that message, if you know the cipher, is the same as the probability of the message. Intuitively, what this equation is telling you is that even if you know the cipher, the probability that you guess the message is equal to the probability that just getting the message in a vacuum. You have no information, you get the message, that probability should be the same as if you do know the cipher and then you're trying to guess the message. Does that definition intuitively make sense to people? Yes? Cool. So are there actually any protocols that satisfy these two definitions? Well, I should hope so. Otherwise, I would be out of a job really quickly. But how do you actually prove these kind of protocols? In particular, that definition of secrecy cannot be so easy to deal with, mathematically speaking. So cryptographers come up with so-called thought experiments or games to make these definitions more willful. In particular, we call this is something we call the eavesdropping game, which is between an adversary, Eve, and an oracle. Okay, the game goes as follows: the eavesdropper comes up with two messages of her choice. She can choose whatever she wants, M0 and M1, gives them both to the oracle. The oracle then chooses one of the two messages, only one, and encrypts that message, right? So you can think of the adversary produces M0, M1, gives them to the oracle. The oracle chooses one of the two messages, say MB, so B is either 1 or 2, sorry, 0 or 1. Obviously, this choice is secret. Computes the encryption of this message, and then gives that encryption to the adversary. The goal of the adversary is to make a guess. Given this encryption, she needs to guess whether M0 was encrypted and M1 was encrypted. You can prove that the definition that we have before on secrecy is equivalent to saying that the scheme is secret if the probability that the adversary guesses which plaintext corresponds to this ciphertext is exactly a half. Okay? So intuitively, what this means is that if you know the ciphertext, the best thing you can do is a 50-50 guess. Right? That the probability that the guess is correct is equal to a half. If you know the ciphertext, the probability that she guesses correctly is as best as a random guess. Is that clear? Cool. So this is actually the definition that is more practical to use when we're proving security of protocols. One such protocol that satisfies perfect security, perfect secrecy, is known as the one-time pad. Okay? Which is, again, a type of symmetric encryption scheme. It consists of a generation algorithm, which on input of a security parameter n, produces a key of n bits. Right? So in this case, the key is going to be some random string of zeros and ones, something like this. For example, the encryption algorithm takes in a message, which is also a string of bits, okay, and performs the operation which we call the XOR. Right? Do you guys know how the XOR works? So we have 0 and 1, 0 and 1. The XOR of 0 with 0 is 0. The XOR of 0 and 1 is 1. The XOR of 1 and 0 is 1. And the XOR of 1 and 1 is 0. So it's basically addition of bits, addition of numbers modulo 2. Okay. The encryption algorithm basically does this. It takes a message, which is a string of zeros and ones, and it takes a key, which is a string of zeros and ones, and it XORs each of the bits. So for example, suppose that the message is, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. Suppose that the message is 1, 1, 0, 1, 1, 1, 1, 1, 1. The XOR of these two things, which is your ciphertext, will be 0 XOR 1, which is 1, 1 XOR 1, which is 0, 0, 0, 0, 0, 1, 1, and then we have 1, 1, 0, and then we have 1, 0, 0, 0. So that's your ciphertext, right? You take each bit and you XOR. Okay? The decryption algorithm, then what it does, when you give it a cipher, it XORs the key again. Yeah? So basically you take this thing and you XOR the key once again. To show that this is a secure cryptographic scheme, we need to satisfy the two properties. It's correct and it is secret. Correctness being that decryption of an encryption is the same message, and secret that the messages cannot be guessed from the ciphertext. Okay, so let's tackle the correctness property first. So we need to show that for any message, the decryption of the encryption M is equal to M. So we just plug and play. So the decryption of the encryption is just going to be K plus N. The decryption of the message of the ciphertext K plus N is going to be K plus N. Because everything is a summation of sorts, you can remove the parentheses, and then you obtain the message again. Why? Can anybody explain that last step to me? So what happens if you go on?
K XOR K will be 0.
Why?
Because it is cancelled out.
Because it cancels out, right? suppose that you have like another copy of the key, 0, 1, 0, 0, 1, 0, 1, 1, 1. What's 0 extra 0? What's 1 extra 1? What's 0 extra 0? Continue. So when you extra the same bits, again, they just cancel. And the same thing happens here. Everything is associative, so you can move the brackets around. So you can move the bracket from k plus m to k plus k, and that just cancels. Right, because then you're XORing the message m with a bunch of zeros. And then you obtain a message. So that is correct. Proved. The secrecy requirement is a little bit more complicated. Okay, the proof. And for this, we recall the eavesdropping experiment, which is where the adversary produces two messages. The oracle produces an encryption of one of the two messages, and the adversary needs to guess which message was encrypted. Okay, and we say that it is perfectly secret if the guess is as good as random, 50-50 guess between M0 and M1. Right. Maybe one thing that I didn't make clear is that that I didn't emphasize, the generation algorithm, which creates the key, creates a completely random string of bits, right? So each of the bits is basically, you can think of as flipping a coin. The outcome of the coin is the first bit, flip it again, that's the second bit of the key, flip it again, that's the third bit of the key, etc. And in fact, the security of the one-time byte hinges on the fact that the key is completely random. The message on the message doesn't have to be, but the key is completely random. So if we go to the eavesdropping experiment, suppose that Eve submits M0 and M1. The oracle chooses one of these two messages, call it MD, and encrypts it. The key observation is that because K, the key, is a random string of bits, the resultant ciphertext, which is the chosen message plus the key, is also going to be a completely random string of bits. Does that make sense? Right? If you take a bit that you want, 0 or 1, and you flip a coin, and you XOR the outcomes, because the flip of the coin was random, the output of the XOR is still going to be random, right? So basically, in the point of view of the eavesdropper, C is essentially a random string of bits. C contains no information about the message because it's a purely random string, which means that the best thing she can do is guess. A 50-50 chance, and we have proven perfect secrecy. Is that clear? Yeah, so then we're done. So to kind of gain some intuition about how the one-time byte works, we have another activity with Lorcan.
Okay, so as Enrique said, the Caesar cipher is not secure because you can just brute force it. So now what I want to do is we'll essentially think of the one-time pad as a Caesar cipher, where we change the orientation of these two circles with every time that we encode a letter. So for example, for the first letter, I could line up A with B, and then encode the first letter of my word. For the second letter, I could encode A with C. So what I would like you to do, and just like, is so I'll say our message is the word quantum, and our key is the word physics.
That's kind of predictable.
So what I want you to try and do is give me the cipher for this message with this key. So for example, the first letter in the message is Q, but the key is P. So that means that I'm lining up P with the letter A, and then I read off what Q is. And then on the second one, I change my key and I read off the second letter. And in this way, you're getting a perfectly hidden message that nobody could ever decrypt. Because if you were to brute force this, you'll get all possible 7-word letters. So everybody just give it a try. And this is like a really basic version of the one-time pad where you don't have to think in binary. If it doesn't make sense, just throw your hand up and I'll come around. So I think we now mostly have it. And I just want to emphasize one more thing, is that you need a completely random key for this to be secure. So in real life, this is not a known word generally.
Awesome. So I think we have the team at the back that was at least the first one to tell me what the encryption is. Can you shout it out? F? Oh, B. Y. Okay, so did everybody mostly understand how this works? So I had some groups that were confused about whether you're actually taking Q to P or U to H. That's not what's happening. P is the key, right? So in the first letter, you take the letter A and you make it coincide with the letter P, and then you find wherever Q is, and you find the corresponding letter, which I guess is F, and that's your first item of the key. For the second letter, your key is the letter H, which means you're lining up the letter A with the letter H, and you're finding the word U, or the letter U, and you read off its corresponding one in the new alphabet, which I guess is D. Okay, and so on. And as Lorcan emphasized, in practice, the key should be completely random. It should not be a word like physics. Yeah, okay, so that's an important thing. It matters, I guess, what wheel you put on the outside and what wheel you put on the inside. But because the decryption basically reverses what you did, it doesn't matter. So they will give you different answers if your encryption wheel is on the outside or on the inside. But when you decrypt, you should still get the same answer. As Lorcan said, like if you're thinking about it in terms of bits, it's the same as instead of adding them up, subtracting them modulo 2. Okay. So basically the example with the Caesar wheel is essentially the same thing with bits, but just instead of using bits, using numbers from 1 to 25, 26? 26. Right, so let's continue. Could I have everybody's attention again, please? Right, so let's continue. Guys over here. Thank you. So the one-time patch, because we have shown that it's perfectly secret, it boasts basically the highest level of security that any cryptographic protocol can be achieved. However, it is extremely impractical, the one-time patch. Can anybody guess why?
They will be changing
Because you need to keep changing what?
the password.
The password, yeah. As the name suggests, it's called a one-time pad. You can only ever use the key once. If you want to encrypt any new message, you need to change the key. The reason being, intuitively speaking, if you have a message M0 and you encrypt it to produce a ciphertext C0 with one key K, and then you have another message M1, which you use the same key to decrypt, to obtain a ciphertext C1. You can obtain partial information about the messages M0 and M1 by summing the two ciphertexts, right? Because in this case, you're going to get M0 plus K plus M1 plus K. And like before, the K and the K cancel. So you have M0 plus M1. And with this, you're able to gain some partial information about the underlying messages. Okay. So basically, you cannot reuse the key. You have to use it the same. You have to use a different key every time you want to encrypt a message with a one-time pad. Another limitation is that the keys need to be very long. The key needs to be as long as the message. If you're sending a very long message, this is very hard to do in practice. Okay, especially when you come back with the problem of how do you distribute these keys if they have to be very long. You fly somebody with a briefcase, apparently is the answer. So maybe we can loosen the definition of secrecy a little bit. Before we said that a protocol is perfectly secret if the probability that an adversary guesses in this oracle game is exactly a half. In fact, there is a theorem that says if you require this level of secrecy, then the key necessarily needs to be at least as long as the message. So maybe this requirement is a little bit too strong. In practice, modern crypto systems, in particular every public key crypto system, uses a weaker notion of security, which is known as computational secrecy. Basically, the definition says that an encryption scheme is secret against adversaries that only have limited time, usually polynomial in size of the size of the key. If the probability that the guess is correct in that eavesdropping game is smaller than a half plus a little bit of wiggle room. So we let their guess be a slightly bit better than epsilon. Okay. For most practical purposes, this is still sufficient. Right? You assume that the adversary is only going to spend some time guessing your password. It's not going to spend for eternity. And if they're able to not break the protocol with that small amount of time, then the protocol is essentially secret for all intents and purposes. Okay. In cryptography, we usually care more about these types of definitions because you can do more interesting things with them. Okay. And that more or less concludes the section on classical cryptography. So now we get to the even more fun part of quantum cryptography. So quantum cryptography in general is the study of cryptographic schemes or cryptographic protocols or primitives that use quantum phenomena. What do I mean by quantum phenomena? Anything that behaves quantumly. A quantum computer, a quantum particle, a photon, a quantum coin, something that behaves quantumly. In general, quantum cryptography is a very broad term. It may refer to post-quantum cryptography, which is the study of classical or quantum crypto systems that are safe against attacks from both classical and quantum computers. One of the, I guess, biggest threats of quantum computers is, maybe you know this, there are quantum algorithms that if you had a powerful enough quantum computer, they would be able to break the classical crypto systems that we currently use today, for which no classical algorithm is known for how to solve them. Using a computer, you can actually break any encryption that we use today. Of course, this is a scary problem. So post-quantum cryptography is the field of study that aims to remedy this problem. Even if you have a quantum computer, arbitrarily powerful, we want to design protocols that are still secure against these quantum computers. Okay. There's also the general study of quantum primitives, primitive for cryptography that utilize quantum phenomena. Okay. Oftentimes, these are the same primitives, something like pseudo-randomness or something oblivious transfer, homomorphic encryption. These are classical protocols. You just put a quantum spin on them, right? Lastly, the focus of today's talk, which will be quantum key distribution. It deals with the distribution of secret keys using quantum phenomena, and the keys will be used for later communication. So it's not a cryptographic protocol per se, like the one-time pad. It's some sort of protocol that allows for the distribution of keys in a way that guarantees that the keys are going to be random and secret. Like for the one-time pad, the key needs to be both random and secret. Okay. Quantum key distribution deals exactly with this problem, or with this task, sorry. So, quantum key distribution, the general setup, it's a communication protocol between two parties, again, Alice and Bob. The way the protocol goes is that they receive some quantum states. Doesn't matter what they are, something that behaves quantumly. They perform some rounds of so-called LOPC operations, L for local operations and public communication. Whereas a local operation means that Alice performs some operations on her quantum states, Bob performs some operations on his own quantum states, then later have some public communication to determine the validity of their operations, if they should abort, what kind of error correction they need to perform. And then at the end of the protocol, they come up with two keys, KA and KB, for Alice and Bob, which they would later use for their own secret communication. So again, we want a quantum key distribution to satisfy some properties. Any guesses from this diagram what those properties might be? Think about same terms as the one-time pad before. Think of correctness and secrecy. What are the two properties that we want this to satisfy, this protocol? There's no message here. They're only trying to generate keys.
Eventually, only the sender and recipient has the keys.
Yeah, precisely. That's one of the conditions. So you want the key to be secret. Even if there is a third party in the protocol that might share some entanglement, which maybe you have learned about earlier today. That is, it's a fancy word for correlation. If you have a third party that is correlated to Alice and Bob, they still will not be able to get any information about the KA and the KB. Another requirement is, again, related to correctness. Alice and Bob are generating keys that they later use for communication. It would make sense if the two keys that they come up with are the same. If they're different keys, then they're not really generating the same key for future communication. Okay. So in particular, a sensible QKD protocol should abort with low probability. So I'm not talking about adversaries yet. It should abort with low probability, namely should be resilient to noise. The noise is a big problem when you're dealing with quantum systems. And if it doesn't abort, the two keys output by Alice and Bob should equal with high probability. Okay. But then, as you suggested, there's also the need to talk about an eavesdropper. Okay, which might be tampering with your QKD protocol. So in QKD, in general, Alice and Bob wish to establish a key, which they will use for later secure communication, in the presence of a malicious eavesdropper Eve. Okay, in this case, a sensible QKD protocol should, if all parties are honest, so if there's no eavesdropper, it should abort with low probability. If it doesn't abort, the keys should be equal with high probability. And note that condition 2 does not require the parties to be honest. So namely, we assume the existence of an adversary. And lastly, if the protocol doesn't abort, the adversary Eve should have very little information about the final key. Okay. But before discussing security decisions, we need to kind of describe the eavesdropper, the adversary. What can they do? What can they not do? Is it strong or is it weak? Right? Ideally, would we want an adversary to be strong or would we want them to be weak? Strong. Why strong? Who said strong? Somebody said it. So why do we want them to be strong?
Prepare for the worst case scenario.
Yeah, precisely. You want to prepare for the worst case scenario. If you assume that the eavesdropper can do a lot, if you manage to prove security against that eavesdropper, then that security notion is a bit stronger than if you assume that they cannot do anything. If you basically assume that the eavesdropper turns around, does not look, and refuses to listen, and you prove security against that eavesdropper, then you're not proving anything, right? There's essentially no adversary, right? So you want them to be really strong and see what you can prove from there. In practice, when you do research, you take a hybrid approach, you see how strong you can make it until you can no longer prove stuff. And then basically you go with your strongest notion. Okay, so in particular, the kind of things we need to discuss when talking about the eavesdropper are the following. Is Eve passive? Can she only listen to the public announcements by Alice and Bob, or can she actually tamper with the operations that they're doing? Does Eve have the power of a quantum computer? Is the quantum computer that the adversary has perfect, or is it very noisy? Does Eve have control of the devices that Alice and Bob, the quantum devices that Alice and Bob use in the experiments? Can Eve intercept and alter the quantum states shared between Alice and Bob? So these are the kind of typical questions that one needs to consider when dealing with like quantum key distribution protocols. Okay. Also, whether she has a quantum memory, which is a hard task in practice. Okay, quantum memory is very hard to build. Okay. So generally, there are two main types of QPD protocols that we talk about. The device-dependent protocols, in this case, the quantum states and the operations that Alice and Bob do on their quantum states are what we call characterized. They're known. Alice and Bob know what quantum states they have, and they know what their measurement devices or operations are doing to those quantum states. Quite remarkably, something that you can do quantumly that you cannot do classically is proof security of key distribution protocols in the device-independent scenario. In the device-independent scenario, you basically assume nothing. The devices that Alice and Bob use are complete black boxes. In fact, you assume that the adversary makes the device with her own instructions, gives them to the honest parties, and then the honest parties basically treat that device as a black box. They put an input and receive an output. They have no idea there's an actual quantum particle inside. They have no idea what type of measurements the devices are making on the supposed quantum particles inside the device. And it turns out that remarkably, you can still generate perfectly secure keys in the case where the devices that the honest parties use are complete black boxes. Okay. And this has to do with, maybe you learned about it in the previous lecture with Fritz, it has to do with entanglement and non-locality. If the devices of the honest party share some entanglement between them, the measurement outputs of some operations that you can do with these devices will be correlated enough, and Alice and Bob can tell that they're correlated enough to rule out any further correlation with the adversary who originally prepared the boxes. That's a very abstract explanation, but maybe we can talk about it a little bit more afterwards. The way your average quantum key distribution protocol will proceed is as follows. In the first stage, the measurement stage, Alice and Bob have all these quantum states, and they perform some measurements on the states. They toss some sort of coin, they produce a measurement input. Based on that measurement input, they perform a certain measurement on the quantum state, and then that measurement will yield an output. From all the measurement inputs and outputs, Alice and Bob will then perform a stage known as parameter estimation, which is basically the step where they determine whether the combination of inputs and outputs are what they expected of quantum particles. And there's some definition of what is to be expected. If it is not what they expected, they can abort the protocol. Then you have a key sifting protocol, which is basically where you use the measurement inputs and outputs to generate a raw key. Then you have an error correction stage, which is where Alice and Bob basically correct the raw keys so that they're the same. And then lastly, you have a privacy amplification stage, which is basically a step that further reduces the information that any potential adversary might have about the raw keys. Okay, this is in general very abstract. So let's talk about some actual quantum key distribution protocols. Well, before that, actually, I guess we need to talk about the definitions. So as we talked about before, a sensible QCD protocol should satisfy three requirements. A so-called completeness condition, which is the probability that the protocol aborts should be smaller than some parameter. We also require some sort of correctness condition. If the protocol does not abort, then the keys output by the honest parties, they should equal with high probability. This is a joint conditional distribution, joint probability distribution. Probability that the keys do not equal and the protocol does not abort should be small, given by some parameter epsilon car. And lastly, secrecy. If the protocol doesn't abort, if the information about the key is small. In mathematical terms, we say that the state output at the end of the protocol containing the key of Alice and any kind of information E that the adversary has, this needs to be close enough to a completely random key and completely uncorrelated information from E. So basically that's what this means. This is the state at the end of the actual protocol, and you want it to be close to a uniformly random key and uncorrelated information from E. Okay, so now we have a choice. We can either talk about the BB84 protocol, which is an example of a device-dependent protocol. Also, I think you will have a quick introduction to BB84 and an actual experiment of the BB84 tomorrow and Friday. And option number two is to talk about a device-independent quantum key distribution protocol based on something called the magic square game. And that actually has to do with research that I did last year. So it's the BB84 protocol is a protocol from the 1980s, 1984, whereas the magic square protocol is from last year, from me. So which one would you guys like to hear about? BB84 or magic squares? Magic square. Okay, so maybe I can start over here while the middle bit is being figured out. So the magic square is something we call in the business a non-local game, the magic square game. So the magic square game goes as follows. You have some referee, which you can think of as the oracle in the experiment before. Oh, nothing with it. Awesome, thank you. And you have two players, Alice and Bob. The way the game goes is that the referee will send Alice a number X, which is either 1, 2, or 3. And it will also send another number Y to Bob, which is either 1, 2, or 3. Their task is to produce 3 bits, A0, A1, A2. Yes, 1, 2, 3. And Bob also needs to produce 3 bits, B1, B2, B3. And in particular, the 3 bits that Alice produces need to have an even parity. What this means is that they need to have an even number of zeros. Sorry, an even number of ones. Okay, so the 3 bits can only be either 0, 0, 0, 0, 1, 1, 1, 0, 1, or 1, 1, 0. Those are the only four possible answers that Alice can produce. Likewise, the 3 bits that Bob needs to produce need to have an odd number of ones. Namely, Bob can only produce 0, 0, 1, 0, 1, 0, 1, 0, 0, or 1, 1, 1. Okay, how do Alice and Bob win this game? Well, Alice and Bob win if you take the white bit of Alice's answer. So if AY is equal to the X bit of Bob. Okay, so maybe diagrammatically this makes a little bit more sense. You can think of Alice and Bob as being given a square grid of 3 by 3. Alice receives a row and Bob receives a column, 1, 2, or 3, 1, 2, or 3. They need to fill that row and the column in such a way that the overlap between the row and the column is the same number. So for example, suppose that Alice gets the first row and she produces the answer 0, 0, 0. And suppose that Bob gets y is equal to 2, the second column, and produces an answer that is 0, 0, 1. In this case, the overlap is the same for both, so they win the game. If Bob had instead replied with, if Alice had replied with 0, 0, 0, and Bob had replied with 1, 1, 1, they would not win the game because they don't produce a matching bits on the overlapping square. Okay? So let's leave it as Bob producing 0, 0, 1. That's an example of a case where they won. So we're interested in what's the probability that Alice and Bob win. And we're interested in this probability, supposing that they're allowed to prepare a strategy before the game begins. So basically, before Alice is given X and before Bob is given Y, they're allowed to prepare some sort of strategy, something that looks like, okay, if I receive X and you receive Y, we output these 3, I output these 3 bits and you output these 3 bits. Okay. Once they receive X and Y, they're no longer allowed to talk to each other. It turns out that if Alice and Bob are allowed to prepare a classical strategy, they can win this game with probability 8 out of 9 times, assuming that X and Y are produced with equal probability each. So the referee generates 1, 2, or 3 with probability 1/3 each, and 1, 2, or 3 Y with probability 1/3 each. Yeah. How does that strategy work? Well, you can think of a possible strategies for Alice and Bob to prepare a completely filled square. So suppose that before the game begins, they say, okay, if Alice receives the first row, she will output 0, 0, 0. If she receives the second row, she will output 0, 0, 0. And then for Bob to be able to win with those outputs, the first column needs to be 0, 0, 1. The second column also needs to be 0, 0, 1. In this case, they always win, right? If Alice gets any of these 2 rows and Bob gets any of these 2 columns, they always win. The problem is what happens with the third row and the third column. For the final row to satisfy Alice's winning condition, Alice's bid condition, this will need to be the number 0. But for it to satisfy Bob's parity condition, this would need to be a 1. Is that clear? Which means they can never fill that last square in a consistent way for the 2 of them. So basically they can share a square that has 8 out of 9 with completely equal overlaps. And then once they can share this square. Once the game begins, Alice will get an X, she will read off that row. Bob will get a Y, he will read off that column. And they win every time unless they get the third row and the third column. So they win 8 out of 9 times. Okay? We're also interested in what happens if Alice and Bob are allowed to prepare a quantum strategy. It turns out, and you're going to have to believe me on this, they can win 100% of the time. Okay, it doesn't matter what X and Y are. They have a strategy using quantum entangled particles that allows them to win 100% of the time. Okay. And part of my research was thinking, okay, what if you add a third player to this game? So suppose now the Magic Square game is played between A, B, and Charlie. C, okay? Again, Alice gets a number X, which is either 1, 2, or 3. Bob gets a number Y, which is again either 1, 2, or 3, a row or a column. And now Charlie, what does Charlie get? That's the axis, not about this. So suppose Charlie actually gets both the row and the column. Okay. Again, the Alice needs to produce 3 bits, A1, A2, A3. Bob needs to produce 3 bits, B1, B2, B3, satisfying the same conditions. So Alice needs to have an even number of ones, and Bob needs to have an odd number of ones in the 3 bits. And Charlie now only needs to produce a single bit C. Okay. Now, Alice, Bob, and Charlie win if once again Alice and Bob have the same overlap in the 3x3 grid. Okay. And if Charlie guesses that overlap. Okay. So basically, once again, Alice and Bob need to generate a row or a column in such a way that the overlap of that row and that column is the same for the both of them. And moreover, Charlie needs to guess that overlap. So for example, if they get row 1 and column 1, Alice can produce 0, 0, 0. Bob can produce 0, 0, 1. And Charlie will need to produce 0 for the 3 of them to win. Okay. So once again, we ask the same questions. What is the probability that Alice, Bob, and Charlie will win if the 3 of them are allowed to prepare a classical strategy? Any guesses? So think of this strategy. Does this classical strategy work in the 3-party case? I hear one no. Why? Well, the point of this strategy is that you basically share a pre-filled square, and then you're rid of that square. Why would that not work for 3 players? It would, right? Alice, Bob, and Charlie can now share this 3x3 square grid, which is complete except for the last entry. And then when they receive an X of Y, and Charlie gets the X and the Y, Alice can just output the X row, Bob can output the Y column, and Charlie can just output the X, Y coordinates. So this also works. And it allows them to win, again, with probability 8/9. Namely, every time that they don't receive the 3rd row and the 3rd column. Okay. But now the difficult part is what's the probability that Alice, Bob, and Charlie win if they're able to prepare a quantum strategy? Any guesses? I hear 1-1. Any other guesses? So the truth is that we actually do not know. We suspect it is actually equal to H/9. The reason we suspect this is because the quantum strategy that allows Alice and Bob to win with probability 1 requires highly entangled particles. It is a fact from quantum mechanics that highly entangled pairs of particles cannot also be highly entangled with a 3rd particle. Basically, Alice and Bob, if they share a highly entangled particle, they're able to win this game. But now that there's a 3rd player, that 3rd player cannot share a 3rd highly entangled state that is entangled with both Alice and Bob. This decrease in the amount of correlation that Alice, Bob, and Charlie can share basically prohibits them from winning with a probability close to 1. In fact, part of my research was trying to find out this probability. We suspect that it is H/9. I could never prove that this is actually H/9 analytically, but doing some smart things, I was able to show that it needs to be smaller than 8.00077 divided by 9. Which is not so bad. Yes, it is. which is sufficient for the purposes of quantum key distribution. Why is it sufficient for the purposes of quantum key distribution? Well, in QKD, it's a two-player protocol, right? You have Alice and Bob playing some quantum game to generate numbers. And they have a third player spying there. You can think of this game as a quantum key distribution between Alice and Bob. Alice will generate a measurement input X, Bob will generate a measurement input Y. They will measure their entangled particles to produce 3 bits, a row and a column, and the overlap will be their bit, right? So in one round of measurements, Alice will measure with X, Bob will measure with Y, and they will then later communicate. And because they win with probability 1 every time, that means the overlapping bits will always be the same for the both of them. So after n rounds of measurements, they will produce n bits corresponding to their respective overlaps, which will always be the same because they produce the same overlap with probability 1. Is that more or less clear how they generate the key? So each time they measure, they produce 3 bits each. And you're guaranteed that with a quantum strategy, these bits will always be the same. That can be your bit that you use for your secret key. Okay, because for 100% of the time, it's the same. Now, the point is, if there was actually a spy involved, the probability drops from 100% to 8/9, which is about 88% of the time. So suppose Alice and Bob do this experiment 100 times, and then they compare the results that they got for the overlap. If the 100 bits they generate are the same, then they're like, okay, cool, we've won this game 100% of the time, no problem. If, however, they only won it 88% of the time, they're like, wait, hold on. We should have been winning this 100% of the time. If we're winning it 8/9 times, that means there's a third player in this game. There's somebody spying on our quantum key distribution protocol. So then they can abort the protocol because they detected all this. This is essentially how device-independent protocols work. You perform some game. Alice and Bob perform some measurements from some entangled quantum particles, and based on the correlations that they produce, they're able to detect and eavesdrop and abort the protocol. Okay, and I think with that, I'm more or less done. Thank you.